No keys, push to start. Yeah. You know what it is. Everything I do it big. Yeah. Screaming that's nothing. When I pulled on the lot, that's nothing. Up in my town, you see me, you know everything. Black and yellow, black and yellow, black and yellow, black and yellow. I put it down from the whip to my diamonds on it. Black and yellow, black and yellow.
What is HPLC actually? High performance liquid chromatography is an essential technique used to separate and analyze components within a mixture. It operates on a highly efficient and precise principle, making it invaluable in scientific and industrial application. First, we see the principle is utilization of a liquid mobile phase. HPLC employs a liquid mobile phase to facilitate the separation and mixture of a component. Second step, we got a dissolution and high pressure flow. The components to be analyzed, known as analytes, are dissolved in a solvent. Dissolution is then forced through a column packed with a stationary phase material under high pressure. Then we got third, a separation process. As the analytes and liquid phase are pumped through the column, separation occurs. This is based on the differential interaction of each component with the stationary phase inside the column. And lastly, we got the detection and chromatogram generation. Detectors at the end of the column identify and measure each component as it elutes. Component as it elutes, the detector response is displayed, and a chromatogram which graphically represents the separation and allows identification and quantification of the components. HPLC is a highly effective method for separating, identifying, and quantifying components in a mixture. Its reliance on a liquid mobile phase and high-pressure system ensures rapid, precise, and versatile analysis. There are three types of objectives in this experiment. First, we got determine the retention time of standard solution, which is caffeine. Second, to identify the caffeine peak in the soft drink sample. And third, to determine the amount of caffeine in soft drink sample using the response factor method.
For methodology of HPLC, high performance liquid chromatography is a technique of separating mixture of compounds based on their interaction with a stationary phase and a mobile phase. It involves preparing samples, preselecting the appropriate mode and mobile phase, choosing the right column, setting up the system, injecting the sample, separating analytes based on their interaction with the stationary and mobile phases, detecting the elute components, and analyzing the resulting data to quantify and identify compounds. The image illustrates the HPLC workflow, starting with the mobile phase being delivered by a solvent pump. The liquid sample is injected and carried into the column containing the stationary phase. Within the column, the components of mixture are separated based on their interaction with the stationary and mobile phases, after which they pass through a detector that converts their presence into electrical signal for analysis.
Of an HPLC system consists of 1. The mobile phase. This is the solvent or eluent that flows through the system and carries the liquid sample from the injector through the column to the detector. The solvent is contained in a reservoir at a higher elevation than the pump to maintain a positive head pressure. A solvent filter removes any particles that could potentially damage the system's sensitive components. 2. A pump. The first piece of hardware the mobile phase encounters is the pump. The pump pushes the mobile phase continually through the HPLC system at a specified flow rate. 3. An autosampler. After the pump, the mobile phase encounters the autosampler. An autosampler works by aspirating and injecting a precise sample volume into the mobile phase stream. The autosampler stores the sample vials or plates in a temperature-controlled environment and injects the sample when instructed by the data system. 4. A column. After sample injection, the mobile phase carries the sample to the stationary phase column, where physical separation of the compound occurs. Proper column temperature control is essential to conserving retention time precision, selectivity, and separation efficiency. 5. A detector. After elution from the column, the mobile phase transports the separated compounds, or analytes, to the detector. Most HPLC detectors work by converting a physiochemical property of an analyte into an electrical signal. And 6. A chromatography data system, CDS. The data system translates the signal from the detector into a chromatogram that provides qualitative and quantitative data about the sample. The data system allows complete control of the pump, autosampler, and detector. All of the instrument parameters, automated run sequences, and data collection are controlled by the data system.
PLC experiment, we have achieved various results of graph for determination from our sample. This is our graph in graph for determination of caffeine in standard Coke. From all the graph we obtain, we can analyze the data and generate a result table that includes the types of compounds, their corresponding retention times, and the peak areas for concentration of caffeine. We need two key formulas. First is the response factor, calculated as the peak area of the caffeine standard divided by its concentration, which is 1 mg per milliliter. Next, we have the formula for the caffeine concentration in the sample, which is the sample peak area divided by the response factor. Remember, the conversion factor is 1 mg per milliliter equal to 1000 ppm. Now, we can start our calculation by using the RF formula. We divide the peak area of the caffeine standard by its concentration, 1 mg per milliliter, giving an RF value of 6,249.48779 mg per milliliter determined, we can now calculate the caffeine concentration in our samples. Starting with Coke sample, we use the formula for caffeine concentration. Divide the peak area of caffeine in Coke, which is 7001.12305, by the RF value we calculated earlier. This gives a value of 1.12027 mg per milliliter. To convert this to parts per million or ppm, we multiply by the conversion factor, which is 1000 ppm per 1 mg per milliliter, resulting in a caffeine concentration of 1120.27 ppm in the Coke sample. Next, we move on. We apply the same process for the Levita sample. Using the formula, we take the peak area of caffeine in the Levita sample and divided it by the RF value. After performing the calculation and converting the result to ppm, we find the caffeine concentration in Levita to be 0.055783 ppm. This process show how we systematically calculate caffeine concentration in different samples using the HPLC data.
I'm AFIF RAHMUNI, and today we will going to discuss about the data that we had collected. The chromatographic analysis of caffeine in the sample shows that both caffeine standard and Coke has similar retention time with 2.4 at 2 minutes and 2.4 at 1 minutes respectively, showing that caffeine behaves similarly in both samples. However, Levita had shorter retention time with 2.019, implementing a potential differences in its composition of the sample. The peak area of caffeine in Coke is much more higher than in the standard, implying that Coke has much more concentration of caffeine rather than in the standard. Unlike Levita, Levita had significantly lower peak area other than the three components, means that it has either much less composition of caffeine or interference from other composition in the sample. Using the RF value that we have calculated, we found that Coke has the highest concentration of caffeine by comparing all the peak area of caffeine between three samples. These results show that the HPLC method successfully separate the caffeine from other component in soft drink, and all the retention time are identified. In conclusion, the analysis highlight the significant variation of caffeine content across the three samples. The release factor of caffeine was found to be 6,249.48779 mg per milliliter, providing a basis for comparison. Coke clearly show a higher peak area of caffeine, indicating much more caffeine content, while Levita show much more lower peak area of caffeine and shorter retention time. This finding show that Levita may have considerably less caffeine rather than in standard and Coke. This is consistent with the fact that in some energy drink like Levita may have less caffeine than in sodas, as they may have other combination of stimulant and ingredient that may influence the caffeine content.